Hello, everyone. Our discussion is about crystallization. It's the seventh module of heat and mass transfer. At the end of this module, you shall be able to comprehend the principles of crystallization equilibria, including solubility curves and supersaturation. And then you're going to apply crystallization principles to engineering design and optimization tasks and solve problems involving crystallization system. So for our topic, we are going to discuss about crystallization. It's found on uh, page 18-48 to 18-53 on the ninth Paris edition. So crystallization, it is a process that is driven by heat transfer. So that's why it's included in this course. So it's a process whereby a solution is supersaturated so as to cause the formation of crystals. It is used in some organic and most inorganic processes that produce powdered solid products. Main purpose is to purify a certain ionic compound. To understand this, we look into the solubility diagrams. So this is an example of a solubility diagram. So solubility diagrams are the equilibrium tool used for solid liquid phase equilibrium. So an example can be seen on figure 18-52 in the ninth edition Paris. Phase diagram of MgSO4 and water. So in the system, as you can see in the system, it is a solution or liquid at higher temperature. So in your y-axis, you have the concentration. Uh, so you have the concentration, and on your x-axis, you have the temperature in Fahrenheit. So if you increase the temperature, the system becomes liquid in phase. But as you cool it down or as you lower the temperature, you begin to form solids. So as you lower the temperature of your system, you begin to form solids. So as you form solid, what happens is that you still have liquid. So as you can see here, you still have liquid or solution phase. But what happens is that um you still have liquid of a strong and stronger composition that is in composition with the solid MgSO4. So you have two phases already present in your system. Or if you are in the other region, you form solid ice or solid water. And that is also in equilibrium with your solution or with your liquid phase. Now, you have these two curves. So where these two curves intersect or come together is what you called eutectic point. So this is your eutectic point. So eutectic point, that is the lowest temperature that produces crystals. So you still get crystals, but it depends on the composition. So it can be pure MgSO4 or pure water. So it depends on the composition. Now, If you get below that temperature, you get both types of crystals. Although they're pure, but separating them is a challenge. So, for example, if you have salt and sugar and you separate them, it's quite challenging. So, um, in the real world setting, usually in our homes, we dissolve sugar in boiling water. And if you keep adding sugar, like for example, one spoonful of sugar at a time, you keep adding sugar until you reach the last spoonful that does not dissolve sugar anymore. Now you cool this mixture and you have what you call supersaturated solution. So there is no more sugar in there than the liquid can hold if it's at equilibrium. So there are few crystals there and it's forming nucleation sites. So as the mixture cools down, those undissolved crystals as as nucleation sites will seem to grow, and you'll have crystals that form and grow larger and larger over time. So in the industry, you need high solute concentration of the mother liquor and rapid cooling. And usually we use seed crystals. Seed crystals to form nucleation. Now, there are several ways to achieve supersaturation. So the first one is um supersaturation by cooling. So you need to cool the solution. An example, an equipment or a crystallizer um example is Swenson Walker crystallizer. So this is the Swanson crystallizer. It can be seen on figure 18-62 on the ninth edition. So for this way, or for this method of supersaturating a solution, you this process utilize um the fact that most solutes have lower solubility when temperature decreased. So from unsaturation solution to nucleation point, so yung seed crystals, they start to form, and they are triggered, those seed crystals, they are triggered further by crystallization once you lower the temperature or once you cool the solution. So another way to achieve supersaturation is through supersaturation by evaporation, through evaporation process of your solvent, or you call it salting out evaporator. So an example is the Oslo crystallizer. So this is the Oslo crystallizer, can be seen on figure 18-63. If you want more information, you can read um your berries. So for this type of crystallizer, the solution is heated and the solvent is vaporized. So you have your vapor outlet here in your evaporating chamber, and then the solution is slightly cooled down. So it's cooled down upon contact with your settling slurry. So here it's cooled down. You have your suspension chamber, and it promotes crystal growth here in your suspension chamber. So here it's a mixed evaporation. This type of crystallizer is mixed evaporation and crystallization. So, it's better because, um, dalawa yung process. There are two processes involved. So, that's why mas malapit niya ma-reach yung saturation point compared with your first crystallizer, which is by cooling only. So the next method for supersaturating a solution in supersaturating a solution is what you called adiabatic evaporation with cooling. So an example to this is your vacuum crystallizer, or specifically your Swanson reaction type draft tube baffle crystallizer, or DTB crystallizer. So it can be seen on figure 18-61. So instead of lowering the temperature for DTB crystallizer, you are lowering the pressure. So this promotes lower boiling point of the solution. So in order to remove a certain amount of solid. So there is no mechanical heat involved. Thus, Q is cancelled for a DTB crystallizer. Next method is in saturating a solution is the addition of a third component to form precipitates. So the presence of additional solute, it will promote precipitation of solids from a saturated solution of a desired solute. So mag-add ka ng other salt, pwede din ng add another amount of the same crystals. So adding a third component where the solubility of your solute is simply reduced by seeding. You call it seeding. And here are the crystallization equipments. So you have your tank crystallizers. So the solution is allowed to cool in open tanks. The mother liquor is drained and crystals are collected. By the way, mother liquor mother liquor is the saturated solution corresponding to a given temperature. So in your crystallization process, you have two products. You have your crystals and then you have your mother liquor. So mother liquor is the saturated solution. So for your tank crystallizers, the solution is allowed to cool in open tanks. The mother liquor is drained and crystals are collected. So you can add cooling coils or agitation. The operation costs are extremely high for tank crystallizers. So it is usually used for small processes, because you're going to process large scale. It's costly. Next is scraped surface crystallizers. So what happens is that the outside is jacketed with cooling coils. And the agitator blade, you have an agitator blade, it scrapes the surface of your crystallizer walls and then it removes crystals as they form. So that is for scraped surface crystallizers. And then next is actually this was already discussed, the Swanson equipment. So another term is a forced circulating liquid evaporator crystallizers. So the liquid circulates through the tube of the steam heater, then into the vapor space of your crystallizer. So there's flash evaporation. So this is where you are adding evaporation process. And at the same time, you have your crystallization process. Swenson. So flash evaporation in the headspace moves the mother liquor towards the supersaturation. The supersaturated liquor flows through a fluidized area of crystals and liquor where crystallization occurs. Product crystals are removed in the recycle. And then lastly, you have the circulating magma vacuum crystallizers. So the crystal solvent mixture is the magma. The magma is heated gently. So again, magma yung term, it is the mixture of crystals and your mother liquor. So the magma is heated gently and mixed back into the vessel. The vacuum in the vapor space causes boiling or evaporation, which forms crystal. So this process is like the adiabatic evaporation with cooling process. So it uses lower pressure. So or vacuum pressure. The crystals are drawn off near the bottom. Now, in crystallization process, in solving, we are going to focus on two main methods, which are shown here. So first is the crystallization by cooling. And then you have the crystallization by adiabatic cooling or vacuum cooling. So for the crystallization by cooling in this method, the solution, you have your solution, you have your feed here. Your solution is cooled. It's being cooled to reduce solubility so that crystals form. So an example to this is you have your pan crystallizer, your agitated batch crystallizer, and the Swanson Walker crystallizer. So you have your feed, it enters into your crystallizer at uh specific temperature, and then you have your solute fraction. And inside your crystallizer, of course, you need your water. So that you have your cooling water. So this is it uses heat exchanger to cool down your solution. So you have your cooling water, it enters at temperature 1 and goes out or leaves at temperature 2. So the solution then after it cools down your system, the solution then separates into your mother liquor. So it is indicated as letter L, your mother liquor, which is the remaining liquid after crystallization, and then your crystals, which is the solid product form. So they have their temperature, TL, and TC, respectively. Now, for crystallization by adiabatic cooling, here there is no heat external heat exchanger used. So you don't need to add um cooler, a cooling liquid. So no external heat exchanger is used. Instead, the system cools itself by evaporation under vacuum pressure. So you have meaning it loses heat through vaporization of part of the solvent. So an example is your vacuum crystallizer or adiabatic cooling crystallizer. So same, you have your feed F, it enters at temperature TF, and then you have the product is your crystals C, and then you have your mother liquor L, which comes out at lower temperature TC and TL respectively. Now, we have these key equations here that are needed for your calculations. So it will help us quantify what happens during crystallization process. Specifically, how much crystals and mother liquor are produced. So you're going to use mass balance or material balance. So how much solute is distributed between them? So you are going to use solute balance or component balance. And how much energy or heat is gained or lost during crystallization. So you're going to use heat balance or energy or enthalpy balance. So overall material balance, you have your feed is equal to your mother liquor L plus C. So F for feed, L for mother liquor, the liquid remaining after crystals form, and then you have your C, which is the crystals form. This equation simply means the total mass in is equal to the total mass out. So no mass lost, it just separates into two parts. Now, for solute balance, you have your X subscript F times F is equal to X subscript L times L plus X subscript C times C. Now, XF, XL, and XC, they are the solute fractions in feed. So XF is the solute fraction in your feed. XL is the solute fraction in your mother liquor. And XC, that is a solute fraction or your crystals. This ensures that the solute or the solid substance dissolved in your liquid is conserved. So that's why you're going to use your solute balance. So now, how to express solute fractions. So basically, your X or the fraction is equal, the solute fraction is equal to the solute over the solution. Now, for hydrates naman, that is the molar weight of your solute divided by the molar weight of your hydrate. This tells us what part of each stream is the solute. Now, if the problem doesn't provide XL or XF, we can get from our solubility data like in Paris. So here, so it's in 9th edition, you have this in your table 2-20. Okay, so how to use solubility data. So here in the table, in the left, here in the left table, it shows the solubilities of inorganic compounds at different temperatures. You can use this to determine how much solute remains dissolved in the solution at a given temperature. Now, don't use it hindi mo siya magagamit diretso. So you need a formula. So the formula that you will use are the following. So you have X solute is equal to 100 S. So, ito, galing to siya dito. So, the S, that is your solubility, which is found in this. Ito, yung nasa table ninyo, that is the solubility, yung data na to. So, at uh at different temperatures you have different solubility. So if let's say at 10 degrees Celsius, so yung solubility ni aluminum sulfate is 33.5 at 10 degrees Celsius. Now, you're going to plug in that value here in order to determine the X solute. So you multiply the S times 100, that is the value of your X solute. Now, si X solute naman, in order to find the solute fraction or your X sub L, in order to find your X sub L, that is the solute fraction in your mother liquor, you are going to divide the calculated X solute, yung na-calculate mo, over X solute times 100. Plus 100, sorry. So, ito, use this formula here. Now we move to the energy side of crystallization. So, Q, or the heat gained by the water, since yung water mo, it's cool, you're going to cool down your feed. So, so si water yung madagdagan ng heat. So, the heat gained by the water, it is equal to the heat removed from your crystals, or it's also equal to UA delta T LM. Since you are going to use heat exchanger, diba? So, you're going to use this log mean temperature na value. Now, this log mean temperature, just like the concept in your heat exchanger, so your log mean temperature difference, or LMTD, it is equal to the difference of the temperature in your feed minus T sub 2 minus the temperature of your mother liquor minus T sub 1. So this one, bale, for example, if you have your counterflow, this is your heat exchanger, your cooler. Ito, this is your feed, and this is the outlet. So, si feed mo, let's say meron siyang 50 degrees Celsius. Ang outlet temperature is meron na cool down na siya to 20 degrees Celsius. Ang inlet ng heat exchanger mo, this is counterflow. So, you have 10 degrees Celsius. Ang outlet ni heat exchanger is 25 degrees Celsius. So, you're going to find the LMTD, or the log mean temperature. So, delta TLM, it's equal to 50, the temperature of your feed, minus 25 minus temperature of your mother liquor, which is 20 minus 10 over ln PF, so 50 minus 25 over 20 minus 10. So, yan. So, that is for your counterflow. So, yan yung i-substitute mo dito to determine the heat gain or the heat loss. See. I'm going to erase this one. And then you have this equation. You have, so diba, Q is equals to MCP delta T. So the weight of your water, CP of water, change of temperature of your water. So see water out, which is the outlet T2 minus the water in, T1, final minus initial, is equal to the heat removed from the crystallizing solution. So you have your F, or that is the flow rate of your feed, times CP of the feed. It depends on what solution you have. And then the final temperature minus the uh um uh no, this is, since it's heat removed, so it's the initial temperature minus the final temperature minus CQC. So what is C? C is the flow rate of your crystals. QC naman, that is the heat of solution. So where can you find the heat of solution, or another term for it is heat of crystallization? So see, heat of crystallization, that is the negative of your heat. The heat of crystallization is the negative of your heat of solution. So, saan mo makikita si heat of solution? It's in table 2-98 in your Paris. So, this is the heat of solution. So, basically, si heat of crystallization or negative lambda C is the negative of your heat of solution. So, pag dito, 6.75, yung heat of solution mo or heat of crystallization is negative 6.1, 6.71 kcal per mole. Take note that the heat of crystallization is the negative of your heat of solution. Heat of solution can be found in your table 2-98. So you are going to substitute that value here for heat of solution. So that is equal to the heat transfer through the crystallizer surface. So you can already, if gusto mo i-calculate si surface area of your crystallizer, you can determine it here. Because your heat gain is equal to the heat loss is equal to UA delta TLM. Now, if the process gives enthalpies instead of temperature, we have this equation here. So if the problem, it gives enthalpies instead of temperature. So we have W, or the flow rate of your water, is equal times the enthalpy of your outlet minus the enthalpy of your inlet, is equal to the flow rate of your feed times the enthalpy of your feed minus the enthalpy of your outlet or the mother liquor, plus the flow rate of your crystals times the enthalpy of your crystals minus the enthalpy of your mother liquor. So this represents the same concept as heat balance. It just it's just expressed in terms of enthalpy. So CHF, that is the enthalpy of your feed. CHL, that is the enthalpy of your mother liquor. HC, enthalpy of crystals. H1, enthalpy of inlet. H2, enthalpy of your outlet. And HL, you have this formula, or the enthalpy of your mother liquor minus the enthalpy of your crystal is equal to the heat of crystallization. Heat of crystallization, which is the negative of heat of solution. Sige. So let's have an example. Okay, so that is the key equations needed for the crystallization process. So let's have an example. For the first one, get the solubility value of magnesium chloride at table 2-20 for 20 degrees Celsius. So you need to get the solubility value. Okay. So let's go back. I'm going to end this presentation. And I'm going to share Paris. So we have magnesium chloride at 20 degrees Celsius. So magnesium chloride here. At 20. So here, this is the temperature at 20. So in order to find the solubility value, so you have your solubility. So 54.5. Okay, let's solve it here. Sure. Mhm. So 54.5. So solubility is equal to the mass of solute over the mass of solvent. I'm sorry. So you have your mass of solvent. And then you have, so you have your, in your Paris, it's 54.5 mgcl this is 54.5 mgcl, this is grams, per 100 grams of solvent. So that is the solubility. Now, in order to convert that solubility, in order to find the value of XL, because you need to find the value of XL in order to calculate your material balance or your solute balance. So XL, it is equal to your um, MS, or the solute mass, divided by solute mass plus ml, or the solvent mass. So the solute mass is 54.5 grams. That is at 20 degrees divided by 54.5 grams plus 100 grams of solvent. So this is 0.35. Your XL, or your liquor fraction, is 0.35. But your solubility value is already 0.545. This is your XL, or the saturated mother liquor concentration. Next, I'm going to erase this. Minutes na lang. Sige. Next one, you have sodium sulfate heptahydrate crystals. And this is this. The second example is you have a 70 grams of 50% solution was seeded with a negligible amount of solid at room temperature to initiate crystallization. How much crystals were covered if the solubility of the solute is 35%? So you have your feed. Sige. Let's first write your given values. So you have your feed, which is 70 grams. And then your XF is 50%, 0.5. And then you have your negligible amount of solid at room, with a negligible amount of solid at room temperature to initiate crystallization. How much crystals were covered if the solubility of the crystals is 35? So you have the solubility of the solute is 35%. So your XL is 0.35. And then your XC is 1%. So because it's pure solute Mansi crystals. Required, how much crystals? So you need to calculate C recovered if the solubility of the solute. So solution, overall mass balance. You have your feed. By the way, let's draw this one, process flow diagram. So you have your crystallizer, and then you have your so yeah, let's denote this as C for crystals, and then you have your L for mother liquor. You have XC, this is 100%, And then you have your XL. XL is 0.35. So overall material balance, you have your F plus CL. F is equal to C plus L. So F is 70 plus C plus L. This is your first equation. Second equation, component mass balance in terms of solute. So you have your XF times F is equal to XC times C plus XL times L. XF is 0.5. F is 70. Is equal to XC is 100 times C plus XL is 0.35 times L. You have two equations, two unknowns. So using your calculator, you can determine your C. So the flow rate of your crystals is 16.15 grams. And then your mother liquor is 53.85 grams. Next. Next problem. Yeah, sodium sulfate heptahydrate crystals are recovered after filtration of magma. Suppose that the said crystals were not pure, that is wet with mother liquor. How much anhydrous sodium, anhydrous, if we're talking about anhydrous, there's no water. Sodium sulfate in total is present in the wet crystals if there is 58% mother liquor and 65 grams wet crystals at 20 degrees Celsius. Okay, so let's solve. First is we draw your process flow diagram. So you have your feed. Feed is equal, your feed, it goes into your filter. So you have your product there, and then you have your magma. And then, no. Sorry. It's not filter. After pa pala si filter. It's not indicated what type of process. But after magma, dyan na pala si filter. So, filter, meron ka daw, after filtration of magma, you have sodium sulfate heptahydrate crystals. So, you have your wet mother liquor. And then you have your crystals. So, how much anhydrous sodium sulfate in total is present in wet crystals if there is 5.8 mother liquor? So your mother liquor is, if there is 5.8 mother liquor in 65 grams wet crystals at 20 degrees Celsius. So si crystal mo, given na siya crystals is 65 grams at 20 degrees Celsius. Sige. So, sodium sulfate. So, let's go to our Paris. If you look into the Paris sodium sulfate, heptahydrate dapat ha. So, dapat yung solid phase natin is naka 7H2O. So, 7H2O. So, sodium sulfate, heptahydrate at 20 degrees Celsius. Meron siyang solubility, sodium sulfate, heptahydrate, 23. So, meron siyang 44. So, let's go back here. Okay. Suppose that the said crystals were not pure, that is wet with mother liquor. How much anhydrous sodium sulfate in total is present in the wet crystals if there is 5.8 mother liquor in 65 grams wet crystals? Mother liquor. Sige. Sodium sulfate. Okay. So, here you have your, 'di ba, 65 grams siya at 20 degrees Celsius. So, 65 grams, meron siyang 5.8 na mother liquor. So, 5.8 na mother liquor. So, 5.8%. So, 0.058 times 65. This is equal to 3.77 grams of mother liquor. Now, this is your L. 3.77. So, next is si XL. Yung nakuha natin is 44. So, 44 divided by 100 plus 44, 144. So, yung XL natin is 0.306. So, bale, ito yung fraction ni solute mo sa mother liquor mo. So, pila man si mother liquor, ay, pila man yung solute mo. So, 0.306 times the mother liquor, 3.77 grams. So, basically, your solute in your mother liquor in total is 1.15 grams. By the way, ang hinahanap pala dito required. How much anhydrous? Anhydrous sodium sulfate. So, anhydrous sodium sulfate. So, nakuha na natin si solute or si sodium sulfate in your mother liquor. So, ito, 1.55 grams. But we're not yet done kasi meron pa tayong hydrous crystals. Kasi 'di ba sodium pentahydrate. So, yung hydrous crystals natin is 99.42. So, 0.9 5% man pala. So, 94.2. 0.942. Sorry. 0.942 times 65. So, that is our hydrous crystals. So, this is equal to 61.23 grams of hydrous. Pero yung hinahanap kasi is anhydrous. So, ito, meron pa to siyang the anhydrous sodium sulfate, Na2SO4, and you have your water kasi naka-hydrous siya. So, in order to get your hydrous crystals, you need to determine XC. Si XC, hindi siya 100% kasi again, hydrous crystals ang naka-indicate. So, determine the XC. We have the formula kanina. Diba? Formula natin is ito. The molar weight of your solute divided by the molar weight of your hydrate. So, molar weight of solute divided by molar weight of hydrate. So, si solute, meron siyang molar weight, si Na2SO4. Na2SO4, meron siyang molar weight na 142.07. Si Na2SO4 H2O times pentahydrate, so 7H2O. Meron siyang 268.07. So, 142.07 divided by 268.268.07. So, your XC is equal to 0.53. So, 0.53, that is your XC. So, XC is 0.53. So, pila man ang anhydrous. So, no water crystal. Ay. This is equal to 0.53 times 61.23. So, this is 32.40. Ay, sorry. 31.45. So, in total, so, hindi pa siya tapos. In total, the anhydrosodium sulfate. So, total Na2SO4 or the anhydrous, so walang water na crystals, is 1.15 plus 32.45. This is equal to 33.6. So this is the final answer. So that's all for our crystallization process. So if you need more examples, you can watch the video below.